In this video, we take a look at chapter 4.1, which is all about vectors. We are going to start by looking at vectors in the plane, what we call R2, the two-dimensional space of real numbers. And then we are going to shift to looking at vectors in what we call Rn, the n-dimensional space of real numbers. We start with R2 because we can actually visualize R2. Rn we're going to have to think about conceptually because I can't draw out 4 or more dimensions for you. And I actually don't do a very good job of drawing 3 dimensions either. Our learning objectives for this chapter are to represent a vector in the plane as a directed line segment, perform basic vector operations in R2 and represent them graphically, perform basic vector operations in Rn, and notice we're not going to try to represent those graphically, and then prove basic properties about vectors and their operations in Rn. In physics and engineering, a vector is an object with magnitude and direction and represented graphically by a directed line segment. In mathematics, we have a much more general definition of a vector. Geometrically, a vector in the plane, and when I say plane, I mean R2. You can denote R2 with just a simple letter R to the second exponent. The second exponent just means 2 dimensions, or sometimes you see the R with 2 lines to the second dimension, so the 2 up in the exponent. Depending on what font I'm using, you'll see both ways written in our slides and assignments. And every once in a while, if I'm in a limited font scenario, I may have to write R with a caret 2 so that you know that that 2 should be up in the exponent. So geometrically, a vector in the plane, which is R2, the two-dimensional real numbers, is represented by a directed line segment with its initial point at the origin and its terminal or final point at x1, x2, or you could call it x1, y1, whichever notation you like to use. The same ordered pair is used to represent the terminal point is also used to represent the vector. So that is, we would say vector x equals x1 and x2. Now notice I'm using bold numbers here to represent vectors. In other texts or handwritten, you might have seen the little arrow on top of the x. So you might say x equals x1, x2. Either notation is fine. And if you know that we're talking about vectors, we may not even sometimes be able to write bold by hand. So we might just say x, but we'll know it's a vector. The coordinates x1 and x2 are called the components of the vector x. And so often we use u and v for vectors. So we'll say vector u equals components u1 and u2 in 2 dimensions on the plane. And vector v equals components v1 and v2 on the plane. And so those 2 vectors are equal if and only if, so this IFF here means if and only if. So both conditions have to be true. U1 equals V1, the first components are a match, and U2 equals V2, the second components are a match. So unless your components are exactly the same, our vectors are not equal. Okay, so here's some illustration of what we've talked about. In my first diagram, here's our initial point down at the origin. And then the terminal point is the ending point x1, x2. It could also be u1, u2 if our vector is called u. And so our vector is labeled right here in the middle with the x. If our vector is v equals -1, 2, we would represent it as in the diagram at right. So you start at the origin and then you plot your point at -1, 2 and connect them up, and that's your vector. So here are the vector operations in R2 or in the plane. These are definitions. So above the equal signs, we've put the DEF short for definitions so that you know these are all definitions of vector operations. So vector addition is component-wise. So if you've got vectors u and v and you are adding them up, then you add each component u1 plus v1 in the first component space and u2 plus v2 in the second component space. If you are multiplying your vector by a scalar, for example, scalar c multiplied by vector u here, scalar c gets multiplied by each component, in this case u1 and u2, of the vector. We're going to see in n dimensions, the same operations apply. So same definitions when we get to n dimensions. A negative vector, for example, if you've got negative u here, each component gets the negative. And so that's the same as saying the negative u vector is -1 scalar times the u vector. So your negative goes through to both components of the vector there. And then if you've got vector subtraction, saying vector u minus vector v is the same as saying vector u plus negative vector v. And so you take the components of u and add to those the negative components of v, or you could say u1 minus v1 and u2 minus v2. And then the zero vector in the plane in R2 is 0, 0, what we think of as the origin. All right, here are some examples. So in our first example here, vector u has endpoint here in quadrant 1, and vector v has endpoint, or we could say terminal point, also in quadrant 1. So when we add them up, it's kind of like averaging the middle distance, and then the vector stretches out to this terminal point u1 plus v1 in the first component and u2 plus v2 in the second component. And then you can kind of visualize for that terminal point here, it's the distance of x being v1 plus u1, and the distance for y being v2 plus u2. So when we're in terminal, or in quadrant 1, the terminal point is also in quadrant 1, and you can really visually see the geometry there. In this second example, we've got vector u down here in quadrant 4, and vector v here at -2, 3 in quadrant 2. And so when we add those up, remember, we're kind of averaging that middle distance. And so we end up with the terminal point in quadrant 1 here, because when we added those up, 3 plus -2 and -2 plus 3 both gave us positive results. Okay, down here in the lower right, here we've got vector u at 1, 4 in quadrant 1, and vector v at 2, -2 in quadrant 4. And when we add those up, again, it's kind of like averaging that middle distance. We end up with a terminal point here at 3, 2. And in this case, because the values were both positive when we added it up in both components, we ended up in quadrant 1. Here on the right in our upper picture, we have vector u, which is at 2, 3. And then if we do 3u, our math is going to be 3 times the vector 2, 3. So that's going to equal 3 times 2 and 3 times 3, or 6, 9 as our new terminal point. So we just multiply through by our scalar there. And then in the bottom right diagram here, we've got vector u with terminal point 3, 1. And then if we want to know, well, what's negative u, that's going to be the negative distributed through to 3, 1, or -3 and -1 for the components. So we end up over here in quadrant 3. All right, this part up top is just where my picture overlapped when I was screenshotting. So that's the bottom of the previous page. And so here now in this left-hand picture, we've got vector u with terminal point 2, 2, and vector v with terminal point 3, -1. So if we do u minus v, those calculations are going to be 2 minus 3 Oh, there should be, okay, 2 minus 3. And then 2 minus -1. So 2 minus 3, that should give us -1. So I'm not sure if either I made a algebra mistake or if this diagram has a mistake here. So 2 minus 3, yeah, that's -1. And then 2 minus -1 gives us 3 here. So I actually think our u minus v should be over here at -1, 3, which it is. It's just a typo right here. That should say -1, 3. All right, there we go. Our picture's okay. It's just to the 5 where it should say -1. Whew. And then if you wanted to think about it as the same as saying u plus -v, you could say, well, here's -v over here at -3, 1. And then you could see if I average -v and u, I get my u minus v at terminal point -1, 3. Okay, I'm going to attempt to draw out some vectors over here on the grid. So this is something you are welcome to practice on graph paper. So I'm going to start here by trying to draw vector u. So vector u has terminal point 2, 4. So I'll just put a point up here. And as best I can with my stylus, oops, already doesn't look so good, so I'll erase that. If we were in a classroom, I'd have a nice ruler to help me here. So I'm just going to do my best. Okay, that looks a little bit better. I'll try to draw an arrow there, and that's u. And now I'm going to attempt to draw vector v. I'll draw vector v in red. So vector v has terminal point at -4, 1. I'll put my terminal point right here, and then just do my best to draw the arrow on here. Not very good, but you can see overall, if this is a straight line, how the vector should look. So certainly my drawing skills aren't perfect, so your drawing skills don't have to be perfect either. And then now we want to find u plus v. So we'll do that one in black. So u plus v is going to be 2 plus -4, so that's going to give me a -2. And 4 plus 1, so that gives me a 5. So -2, 5 is going to be up here. And I believe this because it looks like it's right kind of in between u and v here in the black drawing. And of course, you have to pretend like my line is perfectly straight here. Okay, that looks a little bit closer to reality. And then we've got to find 1.5 times u. So 1.5 times u, we can multiply our values here by 1.5. So 1.5 times 2 is going to be 3, and 1.5 times 4 is going to be 6. So we just put our terminal point here at 3, 6. And you can see it lies on the same straight line as vector u. So anytime you multiply by a scalar, it's just like you're stretching your vector that you already have, so the angle doesn't change. It just extends along the same line. All right, now let's draw -v. All right, I gotta use a color I haven't used much of yet. I'll use green again for -v. So -v, I'm just gonna swap the sign on my values of v. So -v is going to be +4 in the first component and -1 in the second component. So it's actually just a 180 rotation when I find the negative vector here. So here's -v over here. And then last but not least, we're finding v minus u. So let's see, I'll go back to using black because I've used less of that. So v minus u, let me erase my writing down here from earlier. So we've got some space. So v minus u is going to be -4 in the first component, -2 in the first component, and then 1 minus 4 in the second component. So v minus u is going to be -6 and -3. So that will be x is -6, y is -3 down here in quadrant 3. And so that's this vector. And I've drawn a perfectly straight line. Okay, so that's a quick visualization of how you can draw vectors by hand in the plane. And it's very doable on a grid for R2. In 3 dimensions, my drawing is not going to look so good, so I'm going to rely on computer-made diagrams. And then in Rn, we're just going to have to imagine what 4 or more dimensions look like. Let's read about some properties of vector addition and scalar multiplication in the plane. So again, the plane is just 2-dimensional real numbers, or what we call R2. So we're going to let u, v, and w be vectors that are in R2, and then c and d are going to be scalar. So the first property is what's known as closure under addition. So that means if we add up 2 vectors, their result is also going to be a vector in the plane in R2. And if you go back and look at all of our examples, every time we added up these vectors, we saw we stayed in the plane. And you can also think about the fact that if you're in 2 dimensions, adding things in 2 dimensions, there's no way to go down or go up to 3 dimensions. So you're not going to go down to 1 dimension, and you're not going to go to 3 dimensions. Even if you end up with a point, you can still think about the point as belonging to the plane. The second property is the commutative property of addition. So that means we can add in any order. The third property here is the associative property of addition. So that's saying it doesn't matter what order we add in. So you can add u plus v first and then w, or you could add v plus w first and then u. So very often we just write u plus v plus w because of the associativity property. You don't have to worry about grouping your addition with vectors. The next is that we have an additive identity. So an additive identity is something you can add to a vector and it stays the same. So for addition, our additive identity is the 0 vector. So vector u plus the 0 vector doesn't change either of the components. So we say our additive identity is a 0 vector. And then there also has to be an additive inverse, what you can add your vector to and get the 0 vector. So the additive inverse is -u for vector u. Just like for real numbers, these are our additive identity is 0, and our additive inverse is the negative number. All right, property 6, we have closure under scalar multiplication. So what that means is if you multiply your vector by a scalar, the result is still in the plane, or you could say it's still in R2. So we saw in these examples multiplying by scalars, like I did in my hand-drawn diagram, and like we did over here in this example where we multiplied vector u by scalar 3, we still end up with a vector in the plane, which is also known as R2. The distributive property also holds over vector addition, and so our scalar c multiplied by the sum u plus v, vector u plus vector v in parentheses, you can distribute that scalar through just like with the real numbers. So you'd have c times vector u plus c times vector v when you get rid of those parentheses. And then we also have the associativity property, which says if you multiply scalar c by the grouped scalar d times u, that's the same as if you multiplied scalar c and b and then multiplied those by vector u. And then lastly, we have the multiplicative identity property. So the additive identity property is what you can add and not change the vector. The multiplicative identity property is what you can multiply by and not change the vector. So the multiplicative identity is the scalar 1, and that's just the same as for real numbers. So you can prove all of these properties using the definitions we had for the vector operations. So we're going to look at a proof of a couple of these, and then you'll see that you could similarly use the definitions to prove the other properties. All right, so we're going to prove the associative property of vector addition. So if you start with u plus b grouped together and then add w, then using grouping symbols, you keep your brackets around the component-wise addition of u and v. So you've got your u1, u2, and v1, v2, and then that goes to u1 plus v1 and u2 plus v2 still grouped together. And then you're going to be adding w1 and w2. And so then we're going to say, okay, u1 plus v1 grouped then gets added to w1. But we know that you can add in any order with vectors. So that is just the same as saying u1 plus the grouped v1 plus w1. And similarly for the second component with the u2, v2, and w2. And then you can regroup using our definitions. So you could say, well, this is the same as component u1, u2 plus the sums of the v and w components. And so that gives us equality with the other grouping, u plus w grouped together. So we've proven the associative property of vector addition. So to prove the right distributive property of scalar multiplication over addition, we start with c plus d scalars multiplied by vector u, and then we're going to take c plus d and multiply those by each component of vector u, u1 and u2. Then we see, we know we can multiply c times u1 plus b times u1 and c times u2 plus b times u2 by scalar distribution here. And then we've got, we can rearrange and pull out our c's and d's. So we've got here c u1 and c u2 plus d u1 and d u2. And so then we can rearrange that to say that's the same as vector c times u, the scalar c times vector u, and scalar d times vector u. So that is proving the scalar multiplication property, or I'm sorry, scalar addition property 8. Scalar multiplication, the associative property, would be really, really similar in your proof. Okay, in the next video, we'll take a look at vector operations in Rn, the n-dimensional plane, and we'll see that the same operations are able to be extended to n dimensions, and our definitions are compatible in n dimensions as well.